Hi, I'm Jeff Groh, and this is Differential Equations, Exam 5 Review. For problem 1a, we're asked to classify the singular points of a particular second-order linear homogeneous ordinary differential equation as either regular singular points or irregular singular points. The differential equation is x squared minus x, y double prime, plus 1 minus xy prime, plus xy equals 0. To determine how to classify the singular points, we need to first put this equation into standard form, which means we need to divide by the coefficient of y double prime. Let's do that, keeping in mind that x squared minus x is x times the quantity x minus 1. Dividing, notice that x minus 1 is a factor over here. I need to reverse the order of the subtraction. When you reverse the order of a subtraction, you generate a minus sign. You can see that the singularity at x equals 1 cancels out. And x cancels out in the last term on the left-hand side. Nonetheless, the differential equation simplifies as y double prime minus 1 over xy prime plus 1 over the quantity x minus 1, y, equals 0. It is now apparent that the singular points are at x equals 0 and x equals 1. What's left is to classify these singular points as either regular singular points or irregular singular points. Let's work on x equals 0 first. There are two conditions that need to be checked. First, we need to look at x minus x naught p of x to see whether or not multiplying by x minus x naught cancels out the singularity in p of x, yielding an analytic function. In this case, x naught is 0, which means we're multiplying x times p of x being the coefficient of y prime. This simplifies to negative 1, which is analytic, but that only verifies half of the condition, and in particular, analytic at x naught equals 0. There's no singularity at 0 anymore. That's been canceled out by this product. You also need to verify that x minus x naught squared q of x is analytic. Any singularity at 0 is canceled out on q. Q doesn't have any singularity at 0. This is analytic. At 0. Not analytic at 1. There is a singularity at 1, but the analyticity occurs at 0, and hence both of these are analytic at 0. That means this is a regular singular point. By multiplying by these factors, we have increased the regularity of these functions at 0. For x equals 1, we multiply x minus 1 times p of x. This has a singularity at 0, but not at 1. So this is analytic at 1. We also have to multiply x minus 1 squared times q of x. You can see that the singularity cancels out, and we get a polynomial, and all polynomials are analytic on the entire real line. Since both of these functions are analytic at 1, we deduce that x equals 1 is a regular singular point. On problem 1b, things are going to look very familiar, except that I'm going to square this. And one other thing. And we're not going to have a coefficient of x on the y this time. Putting this into the standard form, we'll still have to reverse the order of this subtraction. And when we do, the x minus 1 is going to cancel with one of the x minus 1s here. But we'll still have an x squared after we square. And over here, x squared times x minus 1 squared y. You can see that we still have singular points 0 and 1. Testing x equals 0, you can see that if we multiply by x minus 0 times p of x, you get negative 1 over x times x minus 1. This is still singular at x equals 0. Multiplying by x minus 0 did not cancel out the singularity at x equals 0. This means we don't even need to check the other condition involving q. We know already that this is an irregular singular point. At x equals 1, we need to multiply minus 1 times negative 1 over x squared x minus 1. You can see that the singularity at 1 is canceled out. This is analytic. At x equals 1. Similarly, x minus 1 squared times q of x has the singularity at 1 cancel out as well. This is also analytic at 1. Since both of these are analytic at 1, this is a regular singular point. For problem number 2, we use the method of Frobenius to solve the differential equation xy double prime plus y prime plus xy equals 0. In this case, the standard form is y double prime plus 1 over xy prime plus y equals 0. There is a singular point at x equals 0. Let's check and see if it is a regular singular point. 1, x minus 0 times 1 over x, that's our p of x, is 1. It follows then that the limit as x goes to the singular point 0 of x times 1 over x is 1. And that's called p naught. To check the other case, we get x squared. This is analytic at 0. This is analytic at 0. This is going to be a regular singular point. But we still need to calculate q naught. We're going to the singular point 0 here, this product, and that's 0. So p naught is 1 and q naught is 0. We now need to solve the characteristic equation. which had this form. In this particular instance, we have only this. This r can be factored out, and we get r equals 0. That's a special case, which means that our solution must be analytic. Normally, solutions look like this. The only possible non-analyticities may occur here. Say if r is -1, you'll get division by 0 at x0. But in this case, r is equal to 0, which means this part goes away and we're left with some analytic function. Analytic functions being expressible as power series. In this particular instance, the solution will have the form the sum as k goes from 0 to infinity, a sub k, x to the k. That implies that y prime will have the form the sum as goes from 1 to infinity, k, a sub k, x to the k minus 1. We lose a term because the k equals 0 term is constant, so its derivative is 0. That means this sum must start at 1. Similarly, y double prime must start at 2. We need to put all of this into the differential equation, and it doesn't matter if you plug it into the original differential equation or into the standard form. That when we multiply y double prime by x, we'll end up with one more power on x. We'll have the sum as k goes from 2 to infinity, k minus 1, a sub k, x to the, not k minus 2, but k minus 1, since we're adding on one more factor of x. Y prime is the sum as k goes from 1 to infinity, k, a sub k, x to the k minus 1, and then we have to add on another factor of x on y. And so that gives the sum as k goes from 0 to infinity, a sub k, x to the k plus 1. The plus 1 comes from the extra factor of x, that is the coefficient of y. We need each of the exponents on x to match. This one is the odd one out, so we're going to re-index this sum. We're going to do it in such a way so that the new index, minus 1, is equal to the old index, plus 1. We'll solve this for big K and get K plus 2. We'll also solve for little k and get big K minus 2. These will help us to re-index this third sum. Doing so, we'll have the sum as the new index. If the old index started at 0, the new index will start at 2. The old index and the new index both go to infinity. A sub old k is going to be a sub k minus 2, and we'll have x to the k minus 1 by design. Now all three terms have sums involving x to the power k minus 1. We can equate coefficients on both sides of the equation because all of the powers now match. There's only one little catch, and that is k equals 1 appears here, but both of the other sums begin at k equals 2. So we have to begin by analyzing the k equals 1 case by itself. So if k is equal to 1, we get 1 times a sub 1, and these don't contribute such a term. That has to be equal to the corresponding power on the left-hand side, which is 0. Aha! So a sub 1 must be 0. If k is greater than or equal to 2, all three sums come into play. And we'll have 0 equals k times k minus 1 a sub k plus k a sub k plus a sub k minus 2. The first two terms can combine, and we'll get 0 equals k squared a sub k plus a sub k minus 2. We now have the requisite recursion relation. A sub k is minus a sub k minus 2 divided by k squared. From the recursion relation, we can see that there is an every other one principle. A sub k is not defined by a sub k minus 1, but by a sub k minus 2, 2 back instead of 1 back. That will prove that all of the odd coefficients are 0, because a sub 3 is determined by a sub 1, but a sub 1 is 0, and a sub 5 by a sub 3, and so on. So we deduce that a sub odd are 0 for all odd indices. We have left only to show what happens when the indices are even. Nothing will determine a naught, so a naught will be arbitrary. A2 will be minus a naught divided by 2 squared. Keep in mind, it's best not to simplify these. A sub 4 is minus a2 divided by 4 squared, which is going to be positive a naught divided by 4 squared, 2 squared. A sub 6, you can see, is going to be negative a naught divided by 6 squared, 4 squared, 2 squared. We now need to find a closed form for these even coefficients. Notice that all of these are even, 2, 4, 6. You can factor a 2 out on all of these. You'll have a 2 squared, 2 squared, 2 squared, that's 2 to the power of 6. What's left over is 3 times 2 times 1 squared. You can take a 2 out of each of these factors. Squared. And then you'll have 2 times 1 quantity squared. So I think you can see that as long as you're dealing with even subscripts, a sub 2k, you'll get negative 1 to the k a naught divided by 2 to the power of 2k. 4 will match the subscript here, 6 matches the superscript here. K factorial squared. The solution is then y equals a naught times the sum as k goes 0 to infinity, negative 1 to the k divided by 2 to the 2k, k factorial squared, x to the 2k. We only get even powers on x in this particular analytic function.